So we are going to discuss the main emphasis of these lectures is cosmological perturbations, and we'll begin by discussing some generalities. Then we discuss how we decompose into helicity states, and we'll mostly concentrate in this lecture on tensor modes, since they are particularly interesting and simple. So, okay, in the first place, we are going to deal with linearized theory. The point is that the perturbations in the universe, density perturbations and possibly gravitational waves, have small amplitudes initially. Nowadays, the perturbations are large. There are galaxies where densities are million times larger than average density in the universe, etc. But they all started up from very small in amplitude perturbations. Okay, and this is directly seen in cosmic microwave background. This picture I have shown yesterday. The point here is that, of course, there are warmer and cooler places in the universe, but the relative temperature, relative fluctuations of temperature are on the order of 10 to the minus 4 to 10 to the minus 5, depending on scale. So they are really very small in amplitude, and therefore the linear analysis is actually quite appropriate. So what does it mean? It means that you consider what are our basic equations. Basic equations are Einstein's equations. So you consider Einstein's equations, which is on the left-hand side the gravitational part, 8 pi g delta t mu. Actually, this way is more convenient, t mu. Where g mu is the Einstein tensor. G mu equals r mu nu minus a half of delta mu nu r. So these are Einstein's equations. And also, if you would like to follow the evolution of matter perturbations, then of course you have the linearized conservation law. Covariant conservation of energy and momentum, again, mu nu. Okay, so what one should do is to write down explicitly what all this means, and where delta means linear in perturbation part of the corresponding quantity, and solve these equations, okay, and figure out how the solutions to these equations behave, okay. So let's do that. This is not a very simple story, but let's nevertheless do it. So in the first place, we have perturbations in metric. So let's write down our ds squared, pulling out this scale factor. I will exclusively work in the conformal time. So here we have 8 mu plus h mu dx mu dx nu. So our h mu is the perturbation about homogeneous and isotopic background, okay? Now, one thing to notice is that there is, of course, gauge invariance of general relativity, so that this h mu is not gauge invariant quantities, okay? Now, let me let me write down the gauge transformation, okay? The gauge transformation is this. I call tilde gauge transformed quantities. The standard thing is that g mu nu, which is a squared times 8 mu nu plus h tilde mu nu at x tilde is just the tensorial law, which is dx tilde dx sigma dx tilde nu dx lambda dx tilde nu g sigma lambda of x, okay, where x tilde, where x is x tilde x mu plus psi mu, and psi mu are our gauge parameters. So one works this out at a given value of coordinates, so that this x here is x tilde plus psi, and arrives at the functional form of gauge transformation at a given value of x, or x tilde, you drop tilde, and finally you get that h mu nu equals tilde h mu nu plus d mu psi nu plus d nu psi mu. And since my a here also depends on coordinate time, then we have extra term to a prime over a eta mu nu psi naught. Now there are a couple of things to remember, to understand. One is that we'll always lower indices and raise indices with Minkowski metric, so that, for example, h mu nu is eta mu lambda eta nu rho h lambda rho. Okay, that's definition. So here, for example, psi nu is eta nu lambda psi lambda. Okay, so all indices, after you make this decomposition, all indices are raised and lowered by Minkowski metric. That's one thing. And in particular, this means that g mu nu is a squared times eta mu nu a minus 2, eta mu nu minus h mu nu. And this follows from the fact that the metric and from the fact that the g mu nu g nu lambda equals delta mu mu lambda. Okay, that's definition of inverse metric, and therefore because of that and our convention here, this is the right expression for the metric with upper indices. Okay, so anyway, so this is our gauge transformation, and we will use it to work in some gauge. Okay, that's one thing. Another is that now that's more or less all for the left-hand side. You just sit down, work hard, and calculate the left-hand side here. Okay, the variation of Einstein tensor, its linear part in h mu nu. And you may use some gauge or work initially in arbitrary gauge. Now the left-hand side. The left-hand side, we have to parameterize it. The usual parameterization for the perfect fluid is that T mu nu normally for perfect fluid is P plus rho, remember, times U mu, U nu, minus delta mu nu times P, where P is pressure, rho is energy density. This is for perfect fluid, okay? General expression for perfect fluid, where U mu is for velocity, and U mu obeys the normalization, U mu, U nu equals 1. Okay, this is for velocity of the fluid. Let's work this out for in our case. In our case, this equation here, in our case, what we have is that u mu is 1 over a delta mu 0, meaning that this is the background value, meaning that the for velocity is directed only in time direction for the background. Let me temporarily put this bar for background. Okay. And in general, u0 is a minus 1 times 1 plus delta u0. Whereas the special components denoted by I are small, 1 over a times vi, okay? Where vi is physical velocity, ui is the coordinate velocity, and vi is physical velocity. Why is that so? That's because ui is dxi over ds by definition, where s is the interval along the world line of a particle or fluid element, and physical velocity is just a times dxi divided by ds, right? Because a times xi is the physical length element. Okay, so vi are physical velocities here, and they are small. The fluid moves slowly in the linearized approximation. Okay, so if you look at this normalization condition, then okay, let me first make a gauge choice. A convenient gauge choice here, which simplifies things considerably, is that, well, okay, for the time being it's unnecessary. Anyway, here you have either gij times uj, which is quadratic in small quantities, or you have gi naught, which is small, times vi and v naught, u naught, which is again quadratic because gi naught is small, right? On the background it vanishes. So the only thing that enters here to the linear order is just u0. Okay, and once you plug this in, then you obtain that delta u0 is expressed in terms of h naught naught, minus 1/2 h naught naught. Okay, so this is not independent quantity, whereas vi are independent quantities, and they are not subject to any constraint. Okay, for the time being, they have to be found by solving the equations. Okay. Right, so then we can plug this into the expression for the energy momentum tensor and immediately arrive at the following expression for the perfect fluid. Our p and rho are actually background value, which I temporarily write with a bar, and rho the same, right? Delta rho, rho bar plus delta rho. Okay? So if you plug this expression for velocity in here, then you figure out immediately, since these two are the velocities with upper and lower index, this h naught naught cancels out, so delta t00 is just delta rho. Delta t 0I, you immediately get from here, it only contains this linearized velocity. So this is p plus rho times vi. And I write minus here. There is another convention. Another convention is once you do this 3 plus 1 decomposition, after you do this 3 plus 1 decomposition, like here, then you raise and lower your Latin indices by Euclidean metric. So after you write everything here, then vi is the same thing as vi. Okay? Even though my metric is negative for special components, this is my definition of quantities with lower indices. Okay? So this is minus sign here because I have to first lower this index here with negative metric and then use this convention. That's technicalities, but if you want to really calculate the right-hand side and left-hand side, you have to take care of all these technicalities. Finally, delta t ij, that's the only term that counts here is this one, because for the special components of velocities are small. So this is minus delta ij times p, delta p, change in the variation of the pressure. Okay? This is true for ideal fluid. If you don't want to consider ideal fluids, and you have to, because in reality the fluid in the universe is not quite ideal, especially if you consider small scales, then there is also another term which is called anisotropic stress, minus Pij. This is called anisotropic stress, and by definition its trace is 0, Pi equals 0. So this is traceless tensor, which characterizes how different is your fluid from ideal. Okay, so that's more or less it. For generalities. Now the gauge choice. Convenient gauge choice is that H mixed components 0I is equal to 0. That's a very convenient choice, which makes equations a lot easier than in general. And obviously you can use this gauge freedom to set it equal to 0. But remember, here we have 4 gauge functions, psi mu, and these are only 3 gauge conditions, right? Therefore, there remains a residual gauge freedom. Let's look at this transformation and require that this transformation, which is residual gauge transformation, leaves the mixed components H naught I intact, equal to 0. This will mean that you have the following d naught psi I plus di psi not equals 0. So you have remaining freedom, the same gauge transformations, but with size, the gauge functions subject to this constraint. Okay, we'll use this gauge freedom in what follows. In particular, by the way, one solution to this equation is arbitrary psi I of spatial coordinates only, right? So this obviously will not leave us out from our gauge H naught I equals 0. But not only. There is a functional freedom because, for example, you can take psi naught arbitrary function and figure out what psi I is. Right? So there is one functional freedom of 4 coordinates. All right. Any questions so far? Okay. Now comes helicity decomposition. The point is that our background is homogeneous and isotropic, right? So the first point is that we are going, of course, to solve our equations in Fourier representation, right? So all my functions, for example, delta rho, etc., everything will actually be delta rho of time eta and momentum k times e to the I k x, right? Obviously, what I'm going to get is the equation which is homogeneous in space, and therefore solving it, it's natural to go to Fourier space. Okay? Remember, this k is actually not a physical momentum. It's a coordinate momentum, as we discussed, because x is not physical coordinate. So if I write k times x as k over a times x, this will be physical distances, a times x. So k over a will be physical momentum. Okay? So q, let me call it q, which is k over a, is the physical momentum. Okay? It's redshifts, as we discussed yesterday. Okay, now we will discuss solutions mode by mode, meaning solutions with a given momentum k. Once you have a given momentum k, you break your SO3 symmetry in space, right? You have a directionality of the momentum which singles out some direction for you. However, there remains unbroken a subgroup of SU3, which is SU to SO3, which is SO2, which are rotations around this momentum, right? Little group. So we have remaining SO2 rotations around the momentum. So if here is my momentum k, then my SO2 rotates everything, every quantity around this momentum, okay? And it's unbroken. Therefore, I can decompose my quantities into irreducible representations of this SO2 group, right? And this is just what is called helicity decomposition. Okay? So we can have various helicities here, since we have objects of different tensorial structure. For example, we have vectors like vi, right? And this vector vi could be decomposed into helicity 0 part, which is directed along the momentum. So it's ki, let me call it iki times v, where v is just a scalar, and into part which has helicity 1, right? Which is e I alpha v alpha, okay? Where these are just the polarization vector of photon, right? These are orthogonal to momentum, orthogonal to each other, and unit vectors, right? So arbitrary vector velocity you decompose into a component along the momentum, which is a scalar with respect to rotations, and you decompose it into the the vectors orthogonal to the momentum, and these rotate as the vector in the plane perpendicular to this momentum, right? So that's the helicity decomposition of a vector. You have scalar part, v is a scalar, it doesn't rotate, and this is a vectorial part, helicity 1. Okay. Now, the same for h naught I, but we set h naught I equals 0. How about vectors? How about tensors? We had spatial components of h mu nu, right? Well, it's again straightforward, right? You have hij, and you decompose it into scalar part, meaning that how can I construct a scalar part? I have to make these indices to use the quantities which, even though they have indices, nevertheless they don't rotate along the around the momentum. And that's simple. It's delta ij times some function which which is actually called 2 psi, introducing the notation here. But anyhow, you also have another term which is, let me call it minus, ki kj. Again, this quantity doesn't change when you rotate your frame around the momentum. This goes along the momentum. So let me call it E. And then you have a couple of other terms. One is this one, minus I plus I ki E alpha j plus kj E alpha I W alpha. This is vector, right? It has helicity 1 because these guys rotate as vectors in the plane perpendicular to the momentum. So this is actually a vectorial part. And finally, we have hij traceless and transverse. And this has helicity 2. These are the gravitational waves, right? You describe gravitational waves by transverse traceless components of hij. They rotate by an angle twice the angle once you rotate the plane around the momentum. Okay, so that's the helicity decomposition of the special components of metric tensor. Okay, and correspondingly, all perturbations you decompose into tensor perturbations, right? Which are helicity 2, vector perturbations which contain vectors in the plane perpendicular to the momentum, this one, that one, etc., and scalar perturbations which correspond to helicity 0 components of your perturbations. Okay, that was realized very long ago by Lifshitz in 1946. You can't imagine that people were thinking about cosmological perturbations in 1946, but that was the invention of Evgeny Lifshitz. All right, so today we are going to concentrate on tensor modes. Actually, likewise, you decompose your anisotropic stress tensor, pi ij. So in general, tensor perturbations are sourced by anisotropic stress, okay, or they interact with anisotropic stress. Since all the rest here are either scalars, delta rho, delta p, or vector, transverse part of Vi. So if we are in the perfect fluid approximation, then there is no interaction. Immediately you see that there is no interaction of gravitational waves or tensor perturbations with cosmic medium. They propagate without direct interactions with cosmic medium unless you have some anisotropic stress. And to a reasonable approximation, anisotropic stress is negligible for this purpose, for the tensor perturbations. Although it's not quite. I mean, some, we have different components in the universe. Some are described by perfect fluid very nicely. For example, dark matter. After dark matter particles decouple from conventional matter, they make pressureless fluid, right? They don't move. Their velocities are, the relative velocities in the gas are small, if this is called dark matter. So we're dealing with pressureless fluid, and therefore no anisotropic stress, just a, dust. However, some other components do have sizable anisotropic stress. For example, neutrinos. Neutrinos move fast, essentially with the speed of light until the temperature drops down to their mass. And because of that, it's not perfect fluid at all. They don't interact after they decouple from the conventional matter. They don't interact with anything directly. They move fast. They're not perfect fluid at all, right? And indeed, there is an isotropic stress generated in neutrino component. It's not a very big effect, but they make some effect on, in particular, on the propagation of, on the behavior of tensor perturbations in the universe. The effect is relatively small, and therefore we are going to neglect it, simply because the energy density in neutrinos is always subdominant. It is not negligibly small, but it's small. So, to a reasonable approximation, our cosmic medium is perfect fluid as far as tensor perturbations are concerned, and therefore the equation for tensor perturbations involves only the transverse traceless components of the metric, okay, Hij. By the way, this Hij traceless transverse can also be decomposed into two polarizations, as you know, right? And for completeness, let me write down what they are. So there are Hij transverse traceless can be decomposed into two polarizations, which corresponds to positive and negative helicity, right, of the massless gravitational wave. It's H alpha times Eij alpha, where this Eij is a symmetric tensor, which must be transverse and traceless. And there are two of them. One is called Eij plus, and it can be constructed out of the photon polarization vectors like this: Ei1, Ej1, minus E2I E2j, where E1 and E2 are two transverse vectors, like photon polarization vectors. Okay, obviously its trace is equal to 0 because trace of this is 1, trace of that is minus 1, and also its transverse. What do we need? We need ki eij alpha equals 0 and E alpha equals 0, traceless transverse condition. Obviously, this is also true. Now, the second polarization tensor is 1 square root of 2. This is normalization so that its square of this tensor is 1. It is equal to E1 I E2 j plus E2 I E1 j. It has to be symmetric. It is symmetric. Both are symmetric tensors. Its trace is 0 since E1 times on E2 is equal to 0, and transverse. So there are two polarization tensors. And as far as I should probably say that as far as helicities are concerned, the eigenvalues, the irreducible representation of SO2, then say the vector like A1 plus I E2I, this kind of vector transforms as an irreducible representation of SO2, right? Under the rotation, it goes into, by angle theta, it goes like this. That's what I meant by irreducible representation of SO2 group. Okay, so that's how it goes. Okay, these are circular polarizations of photons. They transform as irreducible representations, and the fact that there is 1 here means that helicity is equal to 1. And the complex conjugate transforms with minus I, and the helicity is minus 1. Likewise, you can construct from these two polarization tensors, you can construct objects that transform with twice this angle under the rotation of the SO2. That's the group interpretation of group theory interpretation of all this construction. Okay, so in this lecture we are going to discuss mainly tensor perturbations, and we have to write down equations for them. So let's do that in the perfect fluid approximation, neglecting the anisotropic stress. And as it's clear then that since we don't have any other tensors, other helicity 2 objects, then there will be equation only for transverse stressless component of the metric. Okay. Well, I had to say, let's see, you didn't ask me, but I have to say that this prime here is always d over d eta. Okay, that's again some conventional notation, convenient notation, because normally dot means derivative with respect to cosmic time, and prime derivative with respect to conformal time. Okay, after I made this decomposition, then the equation for the coefficients H alpha is obtained by calculating the left-hand side of the perturbed linearized Einstein equation. Right-hand side is 0 for the transverse traceless part of the Einstein equation. So you get the following. You get that delta G ij equals 1 over 2a squared d eta squared hij transverse traceless plus 2a prime over a hij dt minus Laplacian of hij dt. That's all. So you plug this expression in the linearized Einstein tensor and you obtain this. And clearly delta G 0I is 0 and delta G 0, 0 is also 0. Because they are not, this is vector, this is scalar. You can't construct vector out of transverse traceless tensor or scalar. Okay? So my field equation, therefore, will be, once I decompose this into the helicity plus and helicity cross, my field equation will be H alpha double prime plus 2a prime over a H alpha minus Laplacian of H alpha, where Laplacian is simply the Laplacian with respect to co-moving coordinates x. As promised, you have the homogeneous equation with coefficients that depends on time, eta. But of course, to solve it, you go to Fourier representation. Okay. Now, eventually, we will need also the action, the quadratic action for transverse traceless perturbations. Again, you can either plug this into the Einstein-Hilbert action and calculate its quadratic part, or you can be smarter. You can be smarter because you know what is the variation of your action. Here it is, with respect to delta H. And since my action is going to be quadratic, then then you know what is going to be the action. Because by varying this action with respect to H, you have to get this expression here. Okay? In any case, the action for the transverse traceless perturbation is the following. Well, remember that the Einstein-Hilbert action had 16 pi g with minus sign integral r square root of g minus g d for x. Okay, that's the way the gravitational coupling comes in. And from that, taking this into account, you get the quadratic part for the transverse traceless perturbations, which is 1 over 64 pi g integral d eta dx d3x a squared d eta h squared minus d h squared, and you sum over polarizations. Sum over alpha. Okay? By the way, this is exactly the same modular overall normalization factor. This is exactly the same as the action for massless scalar field in expanding universe in the coordinates 8 and x. So massless scalar fields minimally coupled to gravity, and gravitational waves behave exactly in the same way. That's a side remark. Okay, so this is our nice equation. Let's discuss its properties. Let me rewrite it in momentum representation. So in momentum representation, my equation is h alpha prime prime plus 2a prime over a h. Let me drop alpha. H prime plus k squared h equals 0. So that's our basic equation. Looks very simple, and it is simple. And now, what are its properties? We immediately see that it's actually an equation for oscillator, right, with friction, time-dependent friction, right? The second term here acts as time-dependent friction. And it is called often Hubble friction. Since my scale factor changes in time, there is some friction term. It will be with us over and over again. So, oscillator with friction, what are the regimes of its evolution? There are two regimes in principle possible. One is WKB, meaning that the second term is small. So my oscillator oscillates with a slowly decaying amplitude because of friction. So this WKB regime occurs when k is much greater than a prime over a, when this friction term here is small compared to the frequency. Friction coefficient here is small compared to frequency of the oscillator. Right? What does this mean physically? Let's recall that the Hubble parameter is a dot over a, right? Now, since dt equals to a d eta for our conformal time, it's in the denominator here, so it's equal to a prime over a squared, where remember prime means d over d eta. Okay? So if I divide this relation here by a, then I get pretty physical result, inequality. K over a should be much greater for WKB regime than h. Okay? This is the physical momentum, right? This is the Hubble parameter. So if my physical momentum is greater than the Hubble parameter, then my oscillator does oscillate. Okay? In other words, the gravitational waves behave more or less in the same fashion as in flat space, with slowly decreasing amplitude. Okay? Remember, this thing here is roughly 1 over lambda, where lambda is the physical wavelength, right? Modulo 2 pi. So this relation here can be rewritten as lambda should be much smaller than h minus 1. Okay? That's another way to say that my waves live in slowly expanding universe. Their wavelength, or inverse frequency, the characteristic time of oscillation, and length, the wavelength, is much smaller than the Hubble scale. Right? Photons here in this room have wavelengths much shorter than the Hubble scale, and therefore we don't really see that they feel the expansion of the universe. Right? This is called, therefore, subhorizon regime. Subhorizon. Since h minus 1 is the horizon size, roughly, the wavelength is shorter than the horizon size, so my waves are subhorizon. The characteristic size of perturbations is smaller than the horizon size. Now, in this WKB regime, you immediately figure out, by solving this equation in the WKB approximation, you find that the amplitude h oscillates e to ik eta divided by a of eta. Okay, that's a simple exercise to write down that h is a slowly varying amplitude. How do you do in WKB? You say that h is a slowly varying amplitude times e k eta. Plug this in here. And neglect second derivatives of a as compared to a prime times k, and then you get equation for a. You solve it, you get this expression. So in subhorizon regime, the amplitudes of gravitational waves decrease inversely proportional to the scale factor. Decrease in time inversely proportional to the scale factor. But that's not the only regime possible for the oscillator. Another regime which is possible for the oscillator is overdamped regime. When the opposite relation holds, when the k is much less than a prime over a, and this means that the wavelength of perturbation is greater than the horizon size. Okay. In the overdamped regime, the situation is different. The oscillatory part, this last term, is negligible here. My momentum is small. So the two solutions, you get the solution that you get a solution which there are still two solutions, but one solution is that h is equal to constant in time. We're talking about the mode of given momentum, so constant means constant in time. And another solution is h prime is proportional to 1 over a squared. Okay? And this solution decays in time. For example, in the radiation domination epoch, a is proportional to eta. So this is 1 over eta squared. So h goes like 1 over a. At meta-domination, a is proportional to eta squared. So this is 1 over eta to the fourth power. So h goes like 1 over eta cube, which is 1 over a 3/2. Okay. And at lambda domination, for example, a goes like 1 over eta. And remember, in this case, eta grows from 0 towards infinity, and here eta grows from minus infinity to 0. And then here I have eta squared on the right-hand side. Therefore, my h is eta cube, which is 1 over a cube. In all these cases, the second solution, this is the second solution, The second solution decays as time goes on. Okay? So there are two modes. One constant mode. This will repeat. This is a nice example on a very illustration on a very simple equation. What's actually happening with scalar perturbations as well. There are two different regimes. One regime is WKB regime, oscillatory regime, or subhorizon regime, and superhorizon regime. And in the superhorizon regime, there is a constant mode and decaying mode. Sometimes this decaying mode, by the way, is called raising mode and increasing mode. And this is because if you go backwards in time, this mode increases. So there is some confusion in, different parts of the cosmological community. Some people call this decaying mode, some call raising mode. But this is the mode that decays as time goes on. This is for superhorizon regime only. So now let's see when these regimes happen. Suppose we are at the radiation domination epoch. At radiation domination epoch, our A is linear, actually in any epoch. This is a power of A is a power of eta, right? At any of these epochs. Therefore, A prime over A prime over A is 1 over eta. Okay? So WKB regime realizes when K eta is much greater than 1. Okay? That's the same thing as here. So if we are at radiational meta domination, eta increases from 0 towards infinity. So at early times, we have the opposite relation, right? This is K eta much less than 1. Right? So at early times, when eta is small, at radiational meta domination, we are in superhorizon regime. Okay? Whereas later on we cross the horizon in, and our waves become subhorizon, shorter wavelengths. The wavelength is shorter than the horizon. Okay? So this is actually relevant for initial conditions of my perturbations, right? That's more or less what I told you yesterday, that the horizon size increases and perturbations which are originally large, superhorizon, they enter the horizon in. So this has to do with initial conditions at the hot Big Bang epoch, right? At the hot stage of the universe. The waves we have, both gravitational waves and also the scalar perturbations, they start off being superhorizon. Okay? Now, clearly, if my perturbations at very early radiation domination epoch are not large in amplitude, then this part, which is decaying mode, will decay towards the horizon entry. Okay? So, if my picture of homogeneous and isotropic universe is approximately correct, then in the beginning, this second mode is small, if not vanishing, and then it will become negligible towards the horizon entry. Okay? So near the horizon entry, the only mode that remains is a constant mode. Okay? So, assuming that my modes were ever superhorizon, I get the initial condition for, in this particular case of gravitational waves or tensor perturbations, that my amplitudes are constant. They are independent of time as you approach the horizon entry. So this is the initial condition. Okay? Because of this initial condition, my oscillations here proceed with a certain phase after horizon entry. Okay? So what I'm talking about is actually maybe too long explanation, physical explanation of what is going on with this equation. This equation at radiation domination, A is linear function of eta, therefore this is just H at radiation domination is just H double prime plus 2 over eta H prime plus K squared H equals 0. You realize this is a Bessel equation, and we want a solution of this Bessel equation which is non-singular at very small eta. As eta goes to 0, we want this amplitude to be finite, right? Otherwise, we have to accept very inhomogeneous, very anisotropic universe at the very beginning of the hot epoch. So for those modes which cross the horizon which become superhorizon at radiation domination, relatively short wavelengths, you have just to solve this equation here and match it to the general solution of oscillatory function divided by A. Okay? After you are subhorizon. Okay? So in this case, this has to do with the solution is H at radiation domination. It's the initial value Hi, which is the initial condition. I'm discussing solutions to this equation, but that's another issue. What are these initial values of the amplitudes? They cannot be specified by just looking at the equation itself. The overall amplitude has to be found from on physical grounds, from the mechanism that generates gravitational waves. But all the rest is fixed. It's k eta divided by k eta. Okay, that's the solution to this equation, which I chose to be non-singular as eta goes to 0. Another solution is cosine, and this cosine k eta over eta is singular, just as I showed. This is 1 over eta. The second solution is singular as eta goes to 0, meaning that initially the universe should have been very inhomogeneous and anisotropic. If you discard this possibility, then that's the solution. Okay? And then, as my universe enters the meta-dominated stage, then it goes like one inverse of the scale factor. Okay, this is scale factor. Eta is a scale factor at radiation domination, but then you have to match it to this solution at later times. Okay, so why is that all interesting and important? Because the gravitational waves, if present in nature, will do all kinds of things to cosmic microwave background. They will influence the cosmic microwave background. And by looking at the cosmic microwave background, as you all very well know, after the Bicep 2 saga, by looking at cosmic microwave background, you can search for Rayleigh gravity waves. Okay. So what we see here now, what is the relevant quantity? It's basically the gravitational wave at recombination epoch. So H at eta recombination is basically Hi times sine k eta. Let me write this like A of eta times k. Sorry. Let me write it like this. K, and let me write it like this. Here is A of eta crossing divided by eta crossing. This expression is valid for the modes which are which cross the horizon in at radiation domination, relatively short wavelength. Okay, I rewrote it. This is triviality at radiation domination, right? So let me first drop this subscript. So this is triviality at radiation domination because A goes like linearly with eta. So this is the same thing as here, right? Eta crossing is sometime at radiation domination. Doesn't matter which time. But then later on it goes like 1 over A. Okay. So we have a nice picture at recombination, right? This amplitude at recombination is here. This is recombination time, the time of photon last scattering. And what we see here is oscillatory behavior, right? This H as function of K, if you assume that this Hi is slowly varying function of momenta or independent of momentum, and inflation predicts then in some sense this Hi is almost independent of momentum, then this is, first of all, oscillatory function of K, provided that your K is large enough, of course, provided that you really cross the horizon in before recombination, right? And as we discussed, it's a constant, non-oscillation, just a constant time independent at low momenta. If your waves did not cross the horizon in before recombination, then their dependence of they are just these constants Hi in the initial values. Okay, so the picture is this. If I write here K momentum and H at recombination epoch for this momentum, then at low momenta is just assuming that Hi is independent of K, then at low momenta you have just flat curve, which is just Hi, the initial value deep in the radiation domination epoch, deep in the early universe, and then you get decreasing, and that's maybe yeah, this is kind of decreasing oscillatory behavior. Okay, this is not correct, sorry. This is wrong. Okay, let me be more h squared. Okay, that's what I'm interested in. So this is constant, and then I have this kind of behavior, right? This is my sign. So I have decreasing amplitude and oscillations with this decreasing amplitude. Decreasing like 1 over k in the end. Okay. And this will translate into properties of contributions due to gravity waves of both temperature anisotropy and polarization of cosmic microwave background. In particular, this flat region that corresponds to the waves that haven't time to oscillate, did not have time to start oscillating, they are overdamped still by recombination. This will be the main part where temperature and anisotropy emerges due to gravitational waves. At higher momenta, the effect of gravity waves is decaying. That's why, by the way, it's very difficult, if not impossible, to observe these gravitational waves at very high momenta by LIGO or LISA, or the gravity wave detectors on the Earth or in cosmos, right? Because they deal with very short wavelengths as compared to the present horizon. They correspond to very high momenta, and the amplitudes of these gravity waves are very small. For the momenta or frequencies or periods of order of, say, or wavelengths of order of 1,000 kilometers, which is typical for LIGO. Okay, it's way out there. Okay, so the amplitudes are there, but they are very small. Therefore, LIGO is not sensitive to Rayleigh gravitational waves, simply because these Rayleigh gravitational waves have died away. They decreased their amplitude very much. Yeah. Yeah, that's the behavior. At very high momenta. No. Again, this is the solution. This is solution for subhorizon at radiation domination. Okay, so assuming that my waves entered the horizon at radiation domination, that's the solution. If k eta is small, k eta much less than 1 will be superhorizon regime. This is just a constant, as we discussed, right? But as if eta, k eta is much greater than 1, then these are oscillations which are damped like 1 or k eta. Okay? And therefore, for high momentum, they are very much suppressed. Okay? Yeah.
This picture is quite tricky for me because we solved the equation for the time. Yes?
Yeah, we did. Yes, that's the solution.
Yes, and actually IHA is constant dependent on k.
Yeah.
On initial condition.
Right. Now the question is what? Yeah.
Why do we have the flat?
Well, we'll come to that later. Inflation predicts flat, in some sense, flat spectrum. In some sense, which will become more precise on later on, this H is a constant. That's a prediction for from inflation. Other, beginnings of the universe can predict very dependent H, the H which depends strongly on K, and typically alternatives to inflation predict that this H increases with K, and but the amplitudes are always very small. So alternatives predict no gravity waves, zero, unobservable. Because high momenta are unobservable because of this effect of damping, and low momenta are unobservable in those cases because there's no generation of gravitational waves at low momenta. So inflation is the only, I think, the only theory that predicts sizable gravity wave background at low momenta, and its prediction typically is that the spectrum is nearly flat. We'll discuss that. All right. Now, I have some time for the digression because we discussed this in more or less theoretical manner. Now the question is, what is this momentum here, right? This momentum divides the modes which are super horizon at recombination and subhorizon at recombination. So it will be, what we are interested in is actually the corresponding angular scale, right? We are having in mind the cosmic microwave background. So it is of interest to see what is the corresponding angular scale. Suppose I have a mode of a certain wavelength corresponding to this k. What is the angle at which I see this mode, right? So what is of interest is the ratio of eta recombination to eta 0, where eta 0 is present value. This is angular scale of the horizon at recombination, right? Remember, this eta is just the horizon size. So this is the horizon recombination. This is the horizon today. So this is the angle at which I see the horizon at recombination, right? Remember our picture with light cones. Okay? So this is the angle of the horizon. I see the horizon at recombination. Okay? So what is this angle? Simple estimate comes if, and it's an estimate, it's not a calculation, but the estimate comes from assuming that both recombination and today are at meta-domination, which is not true. But for estimate, let's assume that, okay? Let's neglect late effect of dark energy, for example. Then my scale factor goes like eta squared at meta-domination. So this ratio is just square root of the scale factor at recombination and present scale factor, right? So it's 1 over 1 plus z recombination square root of. Okay? So remember, today our temperature is roughly 3 degrees. At recombination, it's 3000 degrees. So this is z is 1000, which is true, 1090. It's square root, so it's about 1 over 30. This is a crude estimate. It's not quite correct. It just gives you an idea of what is the angular size of the horizon at recombination, which is how do we see it today? It's about 1/30 of radian. Okay. We can easily refine this. Okay. we can easily refine this by writing that eta is an integral from 0 to time, whatever time is it, dt prime over a of t prime, right? That's our definition of eta, of the distance of the coordinate horizon size. Now let's recall that the redshift is a naught over a at t, so that dz is minus a naught over a dot over a d time, right? This is h. This is dt over a of t. That's precisely what is in here. So my eta can be rewritten in terms of the redshift as the integral from z to infinity dz over a naught h of z. And of course, a naught is an arbitrary number, the present value of the scale factor. You can set it equal to 1, but it cancels out in ratios, right? In this ratio of angular scales, that determines the angular scale. So a naught is not eta, like the scale factor itself, is not quite physical, but ratios of the conformal times is a physical quantity. Okay, now remember that this h of z is h naught times square root of omega meta times 1 plus z cube omega radiation 1 plus the z to the fourth plus omega lambda, right? That's our formula we had yesterday, right? Matter contribution goes like inverse of a cube, etc. So this is the integral, which takes into account both the fact that at recombination we are not very far from equality matter and of matter and radiation, so that at recombination this radiation part, this is radiation, this radiation part is not negligible, and therefore this estimate is incorrect in the numerator. And also this formula tells you the dependence on the fact that you have also the dark energy, the cosmological constant. So it also takes into account that fact. Again, this estimate is wrong in denominator because of the dark energy. But this is an integral. Once you know the values of these omegas, you calculate it, and you end up with the ratio with the angular scale, which is more or less close to what I get. It's about 1 over 50. Okay? So that's the angular scale, refined estimate for the angular scale of the horizontal recombination. And twice this scale, 2 theta h is the diameter, right? 2 eta r. This is the diameter divided by eta 0, and this is 2 degrees. That's what I wrote to you yesterday, that this is 2 degrees. Am I right? Yeah. That's about 2 degrees. Okay, so the overall size of the causally connected region at recombination is seen at 2 degrees. It's also useful sometimes to estimate the ratio of eta at equality to eta 0. Why? Because once you try to analytically understand what do perturbations do, different perturbations do, then this easiest case is when they enter the horizon at radiation domination stage, before equality. And it's much more difficult to study the perturbations that enter the horizon near equality, because then you cannot use very simple formulas for radiation domination nor simple formulas for matter domination. So it's useful to understand that this ratio is about 1 over 120, and the corresponding wavelength, finally, A naught times eta naught. This is the horizon size at present. It is 14 gigaparsec. The waves that were just entering horizon at recombination have present wavelength A naught eta r, which is 280 megaparsec. And those that enter horizon at equality today have size of about 120 megaparsec. So the perturbations whose wavelength is shorter than, say, 120 megaparsec today entered horizon at radiation domination stage, whereas those which have wavelengths greater than 300 megaparsec today, they entered the horizon very recently, after recombination. That's useful numbers to understand. For example, the galaxies, like our galaxy, the corresponding wavelength is actually roughly 1 megaparsec. The matter collapsed into our galaxy from the part of the universe whose initial size was about 1 megaparsec. So these are the modes that make galaxies. Clusters of galaxies, it's more like 10 megaparsec. So they're all entered the horizon at radiation domination epoch. But not very early at radiation domination. You can estimate that even those modes that make dwarf galaxies, they enter the radiation domination at temperatures of few keV, if I remember correctly. All right. So let's see. Yeah, I guess I have to stop here. Okay, I didn't cover vector modes. I will start off with vector modes my next lecture. All the rest I think I have covered.